Here, I'm going to be teaching you how to solve question 16 for the Unit 2 problem set. So, two balls are launched off the edge of a cliff of height h with an initial velocity of v sub 0, which you can also call v naught. The red ball is launched horizontally. The green ball is launched at an angle of theta above the horizontal. Neglect air resistance. Find the following in terms of h, v naught, theta, and constants. So these instructions that they give you at the end are really important. So if you have anything other than these in your answer, it'll be wrong. For example, you don't want to actually use negative 9.8 to solve any of these until part E, when you want actual numbers. For a constant, they mean something like g. So use g instead of 9.8. So let's get started. First, I visualized the problem. So here's what we have here. So the red ball is launched completely horizontally, so it'll make a path something like that. And the green ball is launched at an angle, so it'll have a path something like that. So first, for parts A and B, we only care about the red ball, so just don't even think about the green ball right now. Part A is to find an expression for the time that the red ball is in the air. So I'm going to start with the second kinematic because I remember that normally when solving horizontally launched projectiles, I use the second kinematic, and that's pretty easy because this term always goes away, because if it's a horizontally launched projectile, then the velocity in the y direction starts out at 0. So yf would also be 0 because it's hitting the ground, and then yi is h. That's one of the constants given to us in the problem. And then ay is going to be equal to negative g. So I'll have 0 equals h minus 1/2 gt squared. The next thing I want to do is I'll add this term to both sides. Then I'll multiply both sides by 2 and divide both sides by g. So I'll have t squared equals 2h over g, and then I just take the square root of both sides, and I'll end up with that. So this that I'm circling right here is my final answer to part A. For part B, I want to find an expression for the horizontal displacement of the red ball. That's what I've labeled as xr for the red horizontal distance in this diagram. So again, we want to now use the second kinematic, but this time in the x direction. So this whole last term will go away because there's no acceleration in the x direction. And I just want to, so it's really easy. It'll just be v naught, which is the velocity in the x direction, times the time, which we got from part A. So this is my final answer to part B. We want to do pretty much the exact same thing for the green ball for parts C and D. It's going to be a little bit trickier because it's not a horizontally launched projectile this time. So here's my diagram again. Since this is trickier, I'm going to set up my chart. So in the x direction, even though I don't have any numbers, I can actually still write out what I know. So I know Vix is going to equal V naught cosine theta because some of the constants I'm given are V naught and theta, so it's okay for me to use them within my chart. Viy is V naught sine theta. Ax will be 0, xi is 0. Xf will be equal to xg, so the horizontal displacement for the green ball. And then the time we don't know. Remember, that's what we're solving for in part C. Ay will be equal to negative g. The initial height is h, and the final height will be 0 because it's landing on the ground. So what I can see right now is that I can use the second kinematic to get the time in the y direction. And then I can apply that time to the x direction. Like I said, it's going to look a little bit more complicated because there's more stuff when it's a projectile launched at an angle. So yf is 0, yi is h, etc. I'm going to put this into a slightly different format. So hopefully you guys can recognize now that this is in the form of a quadratic expression. So this is going to be our a term, this will be our b term, and this is our c term. So I'm going to go ahead and just do all that. So we've got negative b, and it'll actually be all of this, that's our b term, and then the t is separate. So it's v naught sine theta plus minus all of this stuff. Yeah, so plus minus b squared minus 4ac all over 2a. So we can simplify this in a couple of different ways. First of all, I can see that I would just want to get rid of this minus sign because I don't want to have a negative time. So I only want to include the plus sign in my final answer. Also, these negative signs will cancel out, so that'll be end up being a plus, and 4 times 1/2 is 2. So this will end up becoming 2gh, and then this will just become g on the bottom. So that's exactly what I have here. So what I've just circled is my final answer for part C. Now for part D, I want to find an expression for xg, or the horizontal displacement for the green ball. And I can clearly see that I can use the second kinematic in the x direction because I've gotten t from part C. So like we did previously, this term will just go away. Vix will be equal to v naught cosine theta, and then t we just get from part C. So it looks pretty messy, but this is what the final answer to part D turns out to be. All of this. Alright, now comes part E, which is not too difficult, except some of the algebra gets pretty gnarly later on. So part E says, if the initial velocity v naught of the balls is 100 meters per second, the green ball is launched at an angle of 30 degrees and the balls land 600 meters apart from each other. What is the height of the cliff? So let's go back to our diagram. So what we have in part D is xg, and what we got for part B is xr. And then what we're given is that the difference between the spots where they land is 600. So hopefully you guys can see that xg minus xr would be equal to 600. So same thing here. This right here is equal to 600. And like I said, we got xg from part D, and we have xr from part B. So we can go ahead and write all of this out. However, at this point it becomes a little bit easier because we have numbers we can plug in. So v naught is 100, theta is 30, and we're allowed to plug in numbers now, so g is equal to 9.8, so we want to go ahead and plug that in. Basically, the only variable we should have left is h, because we're asked for the height of the cliff. So let's go ahead and plug all those numbers in, and then enter stuff into our calculators so we can simplify it. And we can simplify it a little bit more. So I just want to explain a little bit about what I did from this step to this step. So 100 times the cosine of 30 is 86.6. 100 times the sine of 30 is 50. 100 sine 30 squared is 2500, and 2 times 9.8 is 19.6. And then here it was a little bit less straightforward. I did 2 divided by 9.8. I took the square root of that, and then I multiplied that by 100, and that's how I ended up with this 45.175 here. Okay, can do a little bit more stuff to simplify. So I'm going to do the 86.6 divided by 9.8, and then I'm going to distribute that across here. So I end up with this, and then I'm going to simplify it a little bit more by subtracting this 441.837 to both sides. Okay, at this point the algebra is pretty tricky to figure out. I will show it to you, but what I think might be an easier method is to graph this on your graphing calculator and find the zeros. So you would have to subtract this number to that side, and on your graphing calculator you would type x instead of h, but it should give you the same thing. So let me show that to you guys real quick. Here we go. Okay. So I've typed it in ahead of time, so you can see it's just the expression I had on the PowerPoint. And then if you graph it, it'll look like that. So this point right here is our 0. So there's a couple things you can do. You can trace it and then just go along the line until you get to around where y is equal to 0. So it looks like it's around 81. Or you can calculate it by doing this. So press second and then go to that, and then you want to get the 0. So you want it on one side of the 0. So you want the left to be a positive y, so enter. And then you want the right to be a negative y, enter. And then enter again, so it'll guess. And we get 81.22. So that 81.22 is what you should put in for your final answer for part E, if you want to use the graphing calculator method. However, I'm going to go back to the PowerPoint and show you how to solve it algebraically. So this is just what I had on the previous slide, and we want to solve this for h. So with those square roots, I definitely want to get rid of them. So the idea I came up with was to add this to that side because this expression here is complicated. And then from here, I decided to square both sides. So just when you square something, it's the first term squared plus 2 times the terms multiplied together plus the last term squared. So when you do that, you end up with this. So I did this whole side squared. That's relatively straightforward. And then I did this side squared, which you had to use this knowledge here. Okay, we can definitely simplify this quite a bit. First, I'm going to distribute the 78.09 to both sides. Or sorry, not to both sides. I'm going to distribute it through these parentheses. And then from here, I can combine like terms. So I can combine this and this, and I can combine this and this. So I subtracted this from both sides, this right here, and I subtracted this from both sides and ended up here. Now I need to square both sides again, and I end up with this here. So on this side I had to use this knowledge again. Next, I want to put this kind of into a form where I can use the quadratic formula. So I end up with this expression here. So I subtracted this from both sides and then just rearranged it a little bit. So I have my A term, I have my B term, and I have my C term. So I plugged that into the quadratic formula, and I ended up with 81.23. So this is the final answer, and notice that's really close to what we got on our graphing calculators. So that is how you do this problem using your calculator or doing it algebraically.